Hi everybody, and welcome to this FreeFlyer Fundamentals training class. This class is typically taught as a half-day class in a classroom full of students. Since you'll be going through this video at your own pace, you'll probably be able to complete this video and the exercises in less than half a day. This class is intended for people who are brand new to FreeFlyer or for people who want a refresher on the basics. We'll be using FreeFlyer hands-on throughout this training, so if you don't already have FreeFlyer installed and a license set up, please go ahead and do that now. There's additional information in the video description about how to install FreeFlyer if you need any help. Here's the agenda of topics that we'll cover throughout this FreeFlyer Fundamentals training class. We're breaking this video up into 3 parts, and in the first part of this video, we'll talk about navigating the FreeFlyer user interface. We'll talk about setting up and working with the Spacecraft Object, and generating basic output in FreeFlyer. We'll also talk about the FreeFlyer scripting language and the essentials that you need to know to work with FreeFlyer script. We'll also have hands-on examples peppered throughout the training, and in this video we're going to cover part 1 where we'll start building a mission plan, and part 2 where we'll add more output. Let's take a couple minutes to get familiar with the FreeFlyer user interface, especially for people who have never used FreeFlyer before. When you first launch FreeFlyer, you'll see the FreeFlyer home screen. The home screen is divided into different tabs, and I'll run through them quickly. At the upper left, we have the Quick Tasks tab, where you can create a new mission plan, run one of our mission plan wizards, or browse our sample mission plans. The sample mission plans are a really valuable resource. They're divided into subfolders according to topic, and in each of these folders there are examples to help you get started with using all the different functionality in FreeFlyer. Next, we have the Learn About FreeFlyer tab, where we have some links to our help file and a video tutorial link. The help file is another useful resource. For example, on the Getting Started page, there are steps to talk you through setting up a simple mission plan. The Guides and Objects and Functions section of the help file are also really useful resources. Next, the home screen shows the list of files that you've opened recently. And in the center, we have the list of demonstration mission plans that we include with FreeFlyer to really show off some of the more sophisticated features. For example, I'll run this ISS visualization demonstration mission plan. This example mission plan shows the International Space Station in a 2D map and a 3D view as it orbits the Earth. The 2D map shows the location of various ground stations as well as geosynchronous communication satellites. We have a window overlay being drawn that illustrates where the spacecraft is as it's orbiting the Earth. And we also have picture-in-picture 3D view of the ISS showing the ISS solar panels articulating and pointing towards the sun, and we're also drawing the sun vector and the spacecraft velocity vector. Over on the left, we're using the FreeFlyer console window to display information about this simulation. I would definitely encourage you to take a few minutes to run through a lot of these demonstration mission plans so that you can get a feel for the powerful features that FreeFlyer includes. Next on the home screen, we have a section that talks specifically about sample mission plans that show off the new features that were added in the most recent version of FreeFlyer. Then we have our mission plan wizards, and over on the right-hand side we have our contact information and the FreeFlyer tip of the day. We'll continue our tour of FreeFlyer by taking a look at a very simple mission plan. We're now looking at the FreeFlyer control screen. You'll notice that we've switched from the home screen to the control screen. The control screen is made up of 3 main sections. On the left-hand side, we have the object browser. This is where you'll define objects like spacecraft objects and ground stations. You can double-click on any object in the object browser to open up its object editor, and we'll talk more about these throughout the training. On the right-hand side, we have the list of FreeFlyer script elements. This includes commands such as the view command, the plot command, and the maneuver command to maneuver a spacecraft in its orbit. When you're creating a mission plan, you drag and drop these commands from the list of script elements into the mission sequence in the center. The mission sequence is the 3rd main part of the FreeFlyer control screen. This is where we define what the mission plan does when we hit run. In this simple example, we have a while loop with the condition that the while loop will run while the spacecraft's elapsed time is less than 1 day. And then inside that while loop, we're going to view the spacecraft and the ground station and generate a plot. On the x-axis, we'll have the spacecraft elapsed time, and on the y-axis, we'll have the elevation angle from the ground station to the spacecraft object. Finally, we have the step command, which is used to propagate the spacecraft forward in time. Without this step command, we would only see a single static view of the spacecraft and the ground station. The step command is a really crucial part of every FreeFlyer mission plan, because that's how we move the simulation forward in time. We'll talk in a lot more detail in this training about the step command. Just for demonstration, I'll show you how to add a report command into this mission sequence. It's as simple as clicking on the report command and dragging it inside the while loop. I can double-click on any of these commands to access the command editor, and I can choose what I want to report. I have a drop-down list of all of the options associated with the spacecraft object. For this example, I'll just make it a report of the spacecraft's height above the Earth. At the top of the control screen, I have undo and redo buttons, a syntax check button, which I'll talk more about in a second, and then the run button. This runs through the simulation that was defined in the mission sequence. You can see we're generating a 3D view of the spacecraft and the ground station. We have our plot showing the elevation from the ground station to the spacecraft object. And then we have our report of the spacecraft height. At the bottom of the screen, I have a status message that indicates that the mission plan executed successfully. And over on the right, I can see the status is currently that the mission plan has stopped and that the run duration for this mission plan was 9 seconds. You can see that I'm now on the output screen, and I'll navigate back to the control screen. I want to point out one more really important feature. You've seen how we can drag and drop script elements into the mission sequence to access GUI-based editors to let us define what the simulation will be doing. FreeFlyer also provides a FreeForm-based script editor. I can drag and drop a FreeForm section into the mission sequence, double-click on it to edit it. I'll retile the windows here just to illustrate what's going on. Now inside this FreeForm, I can enter any FreeFlyer script, I can call any of these different commands that you see on the right, and I have the flexibility to enter whatever custom logic I want. For this really simple example, I'll start by just entering a map command. This will generate a 2D map of the spacecraft object and the ground station object. You can see how as I type, FreeFlyer shows a list of suggestions to complete the words that I'm typing. So I only have to type a couple of letters, and then I can hit enter to complete that word. I'll go ahead and save my mission plan again. Now I'll use the syntax check button, which I mentioned before. The syntax check button would let me know if I had any typos that I'd entered in my FreeForm script, and then I'll run the mission plan again. Now you can see that we also have, in addition to the 3D view, the plot, and the report, a 2D map showing the spacecraft and the ground station. I also want to point out that each time you run the mission plan, FreeFlyer generates a new workspace. If you want to go back to workspace 1 to look at the results from a previous run of the mission plan, you can just select that tab. Finally, the notes screen provides a place where you can capture notes about your mission plan. That completes our tour of how to navigate the FreeFlyer user interface. Now we're going to dive in with our first hands-on example where we'll start building a mission plan. The first step when setting up a mission plan is almost always to create a spacecraft object, propagate it for some amount of time, and start adding output views and plots. So the plan for this exercise is just to create a spacecraft object and propagate it for 1 day, add some visual output, and just practice navigating around in the FreeFlyer interface. So we'll go ahead and create a new mission plan and save it as FreeFlyerFundamentals.missionPlan, add a spacecraft object in the object browser, drag a while loop from the list of script elements into the mission sequence, then drag a view command and a step command inside the while loop, and run the mission plan. Then we'll navigate back from the output screen to the control screen to continue editing the mission plan. I'll demonstrate working through these steps. I'll create a new mission plan, and I'll go ahead and save it as FreeFlyer Fundamentals. Inside this mission plan, I'm going to add a spacecraft object. We'll just use the default spacecraft object for now. Then I'll drag and drop a while loop into the mission sequence, add a view command and a step command, and run the mission plan. When that finishes running, we'll navigate back to the Control tab. Next, we're going to drag and drop a plot command inside the while loop. You can double-click on the plot command and edit it to plot spacecraft.height on the y-axis. I also want to point out how when you're working with the GUI-based command editors, they show a script preview that shows you the equivalent FreeFlyer script that you would enter into a FreeForm script editor to accomplish the same thing. So this is actually a really great way to learn the syntax of FreeFlyer script. You can even copy and paste the script out of these GUIs into a FreeForm section. After setting up that plot command, go ahead and run your mission plan a second time. Take a moment to practice navigating between the workspaces that are created every time you run the mission plan, and then save your progress. We'll continue to build on this mission plan soon. And to demonstrate how that's done in FreeFlyer, I'll find the plot command in the list of script elements and drag and drop it into the while loop. I'll double click on it and then edit the y-axis so that spacecraft.height is plotted. You can scroll through the list of properties or just type the first letter of the word that you're looking for, like H, and it will jump to that section. As I mentioned, the script preview shows the equivalent FreeFlyer script to generate this plot. Now go ahead and run your mission plan a second time. You should see the 3D view and now also the plot showing the spacecraft height plotted for 1 day. Alright, now we're going to go back and talk in more detail about the spacecraft object, which is really essential to FreeFlyer. As the slide says, the spacecraft object is like a fundamental building block in FreeFlyer. It gives you the interfaces for orbit and attitude propagation, modeling the spacecraft physical bus and the subsystems on board, determining contact analysis with sensors, maneuver modeling, and also for orbit determination. And so we're not going to cover all of that right now, but we'll start by looking at setting up the initial orbit state, setting up the attitude model for the spacecraft, modeling the physical properties of the hardware itself, and then configuring the force model and the propagator that's used. So when you create a spacecraft object and double click on it to look at its object editor, the first page is the orbit page. This lets us define the orbit shape and orientation with respect to the spacecraft's central body. So you can change the starting epoch of the spacecraft, change its central body to any of the planets in the solar system, and you can even add your own custom celestial bodies into FreeFlyer if you want to model a comet or an asteroid or a moon that isn't built into FreeFlyer. And then you can choose what type of orbital element representation, what element type you want to enter, and the reference frame for that orbit state, and then specify the orbit itself. We also have the Orbit Wizard, which provides some nice interfaces for creating a custom orbit or loading an orbit state from a data file. Next, we have the attitude page of the spacecraft object editor, which lets you either choose a custom attitude model or import your attitude from an attitude history file. If you are specifying a custom attitude model, then you can specify the reference frame that's used, and then specify the attitude itself in either Euler angles, quaternions, an attitude matrix, or using a spinner model for your spacecraft attitude. Then if you want to use an attitude history file, then you just select that option to import your attitude, and then browse to the history file either in our FreeFlyer attitude history file format or in the stk.a format. As you're propagating your spacecraft, the spacecraft's epoch will determine what attitude will be selected or interpolated from the attitude history file. So if you try to propagate your spacecraft to an epoch that's not contained within the bounds of the attitude file, then FreeFlyer will just throw an error. Next, we have the spacecraft physical properties settings. This is where you can set the drag area, lift area, and SRP area for the spacecraft, as well as the coefficients of drag, lift, and reflectivity, as well as your spacecraft dry mass and its center of mass and moments of inertia, which are specified in the spacecraft body coordinate system. When you're propagating your spacecraft in FreeFlyer, you've already seen this briefly as we were putting together our simple starter mission plan. You'll use the step command. Any spacecraft in FreeFlyer can be propagated using either an integrator or by using an ephemeris file. We can accomplish this by going to the propagator page under Motion Model on your spacecraft object. Every spacecraft that you add into your FreeFlyer mission plan can use a different propagator if you want it to. You just select for that spacecraft object the motion source, whether it's an integrator or a type of ephemeris. And then when you're using an integrator, just specify the integrator type. The default is the Runge-Kutta 8.9, which is the highest accuracy integrator in FreeFlyer, or you can choose a simpler model like a 2-body or J2 mean analytic propagator. Next, you'll choose your integrator step mode. If you choose fixed step size, this will ensure that all of your output data will be updated at a regular interval. If you specify a positive step size, then FreeFlyer will propagate the spacecraft forward in time, and a negative step size will propagate the spacecraft backwards. On the other hand, if you want to use a variable step size, this lets FreeFlyer increase and decrease the propagation step size dynamically behind the scenes based on the error tolerance that you specify. This can potentially improve the runtime speed of your mission plan because FreeFlyer is able to take larger steps sometimes. On the other hand, this will mean that your output data won't be reported at regular intervals. It's important to remember that in both step modes, FreeFlyer always respects that relative error tolerance that you specify, and so intermediate integration steps are always taken behind the scenes even when using a fixed step size to ensure that the local error doesn't grow past the value that you set. On the Force Models page of the Spacecraft Object Editor, you can specify the forces that will be integrated in the spacecraft's motion model. You can check the boxes to include the gravitational force from any celestial body. When the Earth is selected, you can configure not only the Earth's gravitational field, but also the Earth atmospheric forces of lift and drag. You can also turn on solar radiation pressure. FreeFlyer also includes ways to let you specify user-defined forces to include in the force model. That's a bit more of an advanced topic, so we won't go into detail on that in this training, but there's a lot more information about that in our FreeFlyer help file. Once you've decided that you want to include the gravitational effects of a particular body in your spacecraft's force model, you can choose what type of model to apply. You can choose a simple point mass gravitational source, or a more complex spherical harmonic representation of the gravity, where you specify the number of zonal and tesseract potential field terms representing the gravitational force. You also have the option to include solid tides in the force model. FreeFlyer also includes a variety of different gravity model data files that you can choose from. You can see the gravitational models that are included for the Earth, Moon, Mars, and Venus here. If you have a different gravitational data source that you want to use, all you need to do is format that data into the file format that FreeFlyer expects. That format is documented in our help file. When you're configuring the Earth's atmospheric forces, you can turn on lift and/or drag, and you can choose which atmospheric density model to use. On the other hand, if you don't want to configure a force model and use an integrator to propagate your spacecraft object, you can choose to use an ephemeris file. You might have an ephemeris that captures a trajectory that's already been computed, whether by FreeFlyer or by some other tool. If you want to import that trajectory into FreeFlyer, just choose ephemeris for the motion source on the spacecraft propagator page, and then browse to the ephemeris file. FreeFlyer supports our own FreeFlyer ephemeris format, as well as STK ephemeris files, CCSDS OEM files, SPICE ephemerides, as well as some other formats. When you're using an ephemeris as your spacecraft's propagator, you can set the ephemeris step mode. The first option is to step to the ephemeris points that are captured in the file. In this mode, when you call the step command, FreeFlyer will propagate the spacecraft from one state vector to the next from the state vectors that are contained in the file. On the other hand, if you use the fixed step size option, then FreeFlyer will interpolate the states in the ephemeris file if you attempt to step the spacecraft to an epoch that doesn't land exactly on one of those state vectors in the file. When you're working with an ephemeris file in fixed step mode, a positive step size will propagate through the ephemeris forward in time, and a negative step size will let you go backwards. So now we've taken a close look at about the first half of the pages in the Spacecraft Object Editor. We'll talk in more detail about the different subsystems on the spacecraft object and the orbit determination settings in other FreeFlyer training tutorials. Now we'll talk about the different ways to easily generate output windows in FreeFlyer. Over the next few slides, we'll talk about the different view commands that can be used to easily and quickly generate output windows in FreeFlyer. These commands don't give you a whole lot of configuration options on the output windows that are generated, but later in this FreeFlyer Fundamentals training, we'll talk about how to create more customized output windows as well. The view command displays objects in a default 3D Earth-fixed viewpoint. You can specify any number of objects to be viewed, separated by commas. The map command will display objects on a 2D equidistant rectangular projection of the Earth. Later on, when we talk about configuring more customized output windows, you'll learn how to control every aspect of a 2D map or a 3D viewpoint. The map command isn't shown on the list of script elements in the FreeFlyer control screen on the right-hand side, but you can access the map command by dragging and dropping a view command into your mission sequence. Then double-click the view command to edit it and change the view type to 2D map. The plot command is used to generate an XY plot. The first parameter that you specify will be on the x-axis, and then any additional parameters that you specify will be plotted as separate series on the y-axis. FreeFlyer includes a few different variants on the plot command. First, we have the monitor command, which creates a scrolling XY plot. This is useful if you have a plot of telemetry values that are streaming down from your spacecraft, and you only want to plot the most recent values, say for the last hour or the last day. Through your user preferences settings, you can control the number of points that will be displayed in this scrolling window. The polar plot command can be used to display series on an R theta plot, and the polar monitor command lets you create a polar plot that displays only the most recent streaming data values. To access the monitor, polar plot, or polar monitor commands, simply drag and drop a plot command into the mission sequence, and then edit the plot command to change the plot type or the monitor mode. The watch command can be used to generate a window that displays the current values for a list of parameters. The screenshot at the bottom of this slide shows an example of what the watch window will look like. Each parameter that you watch will be shown on a separate row. You can use qualifiers to control the color of the text that's displayed. By default, the text will be black, but you can also set a specific color to be used, or you can set error bounds, where the text will be green if it's within the bounds and red outside the bounds. Or you can specify error and warning bounds, so that the text will be red, yellow, or green depending on the current value of the parameter. Again, this is useful if you're generating displays where you want to keep an eye on streaming telemetry data, or even simulated data, and you want a visual indication of whether the values are in their expected ranges. The report command can be used to generate a data table of values that's displayed on your screen. Each parameter that you specify will be reported as a separate column. You can also use the report command to report data out to an output file or to the FreeFlyer console window. The image at the bottom of this slide shows an example of an output file generated by FreeFlyer. By default, FreeFlyer will include the header, line feeds, and the pad to keep the columns aligned. You can also turn off those formatting features through the report command by using the keywords without headers, without line feed, and without pad. I also want to mention the FreeFlyer report interface object. The report interface can be used to collect data at various points within your mission plan and generate a single output file. The report interface also gives you the option to append new data to the end of an existing file. The FreeFlyer script shown on this slide shows how you would set the output file name for a report interface object, configure the report interface object to append data to the file if it already exists, then report the spacecraft epoch text to the report interface without headers, then report the spacecraft semi-major axis and period to the report interface, and then use the close command to release the lock on the file. I mentioned the FreeFlyer console window a few slides ago. The console window can be used to describe what's happening in a mission plan while it's running. There's a console window object called console that exists automatically in every mission plan that you create. You can also create additional console windows if you want to have different pieces of information being displayed to different windows in your output screen. You use the report command to report values out to the console, and you can report any combination of text and numeric values. The left-hand image shows an example of what a console window might look like, and on the right we see the console object editor that lets you configure how the console appears. Next, we'll take a couple minutes to talk about the essentials of FreeFlyer script. FreeFlyer's scripting language is one of its most powerful features. The fact that there's a built-in scripting environment built into your orbital simulation software means that you have unlimited control over every aspect of your simulation. Through FreeFlyer scripting, you can define complex flow control logic to model your mission-unique scenario and calculate parameters of interest to your specific spacecraft or ground segment that might not be built into FreeFlyer. Additionally, some of the more advanced FreeFlyer features that are built in aren't accessible through the GUIs, that is, the object editors and the script element editors, and so they can only be used inside of FreeForm script editors. So it's a good idea to start getting comfortable with using FreeFlyer script sooner rather than later. When you're working inside a FreeForm script editor, FreeFlyer works to make it as easy for you as possible. The FreeForm script editor provides autocomplete functionality and syntax checking to make your scripting fast and easy. You can get started by dragging one or more FreeForm sections into the mission sequence from the list of script elements on the right-hand side of the control screen. The image shown here shows an example of typing inside a FreeForm script editor and the autocomplete menu that appears as you type. All you need to do is hit Enter or Space to complete the suggested word. The image also shows an example of the right-click context menu that you get if you right-click inside a FreeForm script editor. There are a lot of useful features here, in particular the Go To definition, Find All References, and Go To Help File buttons are extremely useful. As you're building up the mission sequence of your FreeFlyer mission plans, you'll often end up having several different FreeForm script sections, as well as potentially several different GUI-based mission sequence elements like a while loop or a step command that you drag and drop into the mission sequence. I want to point out that at the top of the mission sequence tab, there's a little down arrow that lets you select the option to view script overview. This will give you a combined view of all of the FreeForm sections and the GUI-based script elements in your mission sequence so that you can see the whole simulation script in one snapshot. I also want to point out that you can right-click on lines in the mission sequence to convert them into FreeForm script editors. Now we'll talk a little bit about the syntax of working with objects in FreeFlyer script. To create an object in FreeFlyer script, all you need to do is type out the type of object that you want to create and then the instance name that will be used. These examples show how you would create a spacecraft object called Spacecraft 1, a ground station object called GS, and a variable object called maxAlt. Once you've created your FreeFlyer objects, you'll see that they can have properties and methods that are associated with them. An example of a property is the spacecraft.a property, which gives you read and write access to the spacecraft's semi-major axis. An example of a method is the spacecraft.contact method. Methods can have more than one overload that let you specify different arguments into the method. Here we see that the spacecraft.contact method has two different overloads that let you specify either a ground station object or a region object as the argument. This is just some useful vocabulary to be aware of if you're new to scripting languages. FreeFlyer includes a few different features to help you understand what's going on inside your FreeFlyer script. One useful feature is that you hover your mouse over a property of an object. FreeFlyer will display detailed information about that property. In this example, if we hover the mouse over the spacecraft.EulerRates property, we can see the description of that property, the type, the access, which is read or write, the units, and the default value. Similarly, when we're calling a method, FreeFlyer will display detailed information about the method overloads, and each argument that need to be passed into the method. When you're typing in a FreeForm script editor, there are a few shortcuts that are good to know about. You can use either Enter or Control Space to finish a partially typed script element, and you can use Control Shift Space to reopen the method description window if you've navigated away from it. FreeFlyer objects can also have child objects that can have their own properties and methods, but are accessed through the parent object. This script shows an example of adding a sensor child object to a spacecraft, and then accessing the sensor child object through the spacecraft.sensors array, where we're using the array index of 0 to access the first sensor in the array and report its cone half angle. This diagram illustrates the different child objects of a spacecraft object. The spacecraft is a complex object, and it uses child objects to organize the properties and settings for its propagator, for thrusters, tanks, and sensors, for its OD settings, and more. The diagram also shows how we can have multiple sensor child objects, which are accessed through the sensors array, and each one of those can have multiple properties and methods. This slide is a useful reference, and it shows the syntax for the most common flow control statements that you'll use in FreeFlyer: the while loop, the for loop, and the if statement. FreeFlyer also supports try statements, switch case statements, break and continue statements, as well as the pause and stop commands, and the while stepping and while maneuvering commands. There's details on all of the syntax for using these statements and commands in the FreeFlyer help file. Next, we have a few other useful notes to remember about working with FreeFlyer script. It's important to remember that every line of FreeFlyer script needs to end with a semicolon, and you can create comments in your script using 2 forward slashes to comment out a line, or you can create block comments using the /* syntax that you see here. In our hands-on example, you've already created an instance of a spacecraft object, which is probably the most complex object that exists in FreeFlyer. But now we want to take a second to go back and talk about the most simple objects in FreeFlyer for storing basic data. The variable, array, and matrix objects in FreeFlyer are used to store numeric values. The string and string array objects are used to store text values, and the timespan and timespan array objects are used to store time values. When you're working with an array, matrix, or a string array or timespan array, you'll use square brackets to access the elements inside that array. All indices in FreeFlyer start from 0, so you can access array of 0 to access the first element in the array. You can also assign all the values to an entire array at once using curly brackets with commas separating the values. And you can assign all the values to a matrix object at once using square brackets with commas to separate the values and semicolons to separate the rows. Let's take another second to talk about timespan objects. Times in FreeFlyer can be stored down to an accuracy of the nanosecond level, and so we need a special data type in order to store time values. Some examples of timespans in FreeFlyer are the spacecraft.epoch property and the spacecraft.elapsed time property. When you are assigning the value of a timespan object, you can use a literal timespan declaration, where you use the keyword timespan in all caps and then specify the value in days, hours, minutes, seconds, milliseconds, microseconds, or nanoseconds. You can also use a static method to set the timespan value. The static method timespan.fromDays is an example where you can specify the value in days, but there are also static methods that let you specify the time in hours, minutes, seconds, or fractional seconds. When working with these basic data types, there are various built-in functions that provide useful math operations, as well as orbit state conversion functions to let you convert spacecraft orbital elements between different element sets, or converting the orbit state to different reference frames. There are also built-in functions for converting between different time systems, such as UTC, TAI, GPS time, or between different local time zones. Finally, there are also functions that let you easily convert between calendar-formatted strings and variables representing epochs and timespan objects. The script examples here show some examples of converting from a variable object to a timespan, as well as converting from a string representing a calendar date to a timespan. Now get ready to jump back into FreeFlyer because we're going to add more output into our hands-on example. As I've mentioned, the spacecraft object is a very powerful object in FreeFlyer that contains a lot of really useful functionality. It contains interfaces for reporting all different sorts of information about the spacecraft's orbit and the orbital environment. Let's go ahead and use some of those built-in features on the spacecraft object to add a few more interesting plots and reports into our mission plan. In the next few minutes, we will add a report of the spacecraft's orbital elements over time. We'll generate a plot of the spacecraft's orbital geometry. We'll add a 2D ground track view. We'll save a shadow times report out to a file, and we'll color code the orbit depending on whether the spacecraft is in light or shadow. Take a moment to add this report command into your while loop. You can either drag and drop a report command into the mission sequence, or type this report command into a FreeForm script editor inside the while loop. This report will show the spacecraft's current epoch and its Keplerian orbital elements. Once you've entered this report command, go ahead and run the mission plan to see the output. I'll go ahead and add this report command using a FreeForm script editor. I'll drag and drop a FreeForm section into my mission sequence. It's important for the FreeForm to go inside the while loop. It doesn't matter exactly where inside the while loop, but it's generally a good practice to keep all of your commands that are generating output together, and then your spacecraft propagation step command at the end. I'll double click to edit the FreeForm. I'm going to set a label for the FreeForm. I'll just call it report command. You'll notice as you're typing in FreeForm that you really only have to type a few letters before FreeFlyer will offer you the suggestion to complete the word that you're looking for. Once you've entered the report command, remember to save your mission plan. You can use the syntax check button to make sure you don't have any typing errors, and then go ahead and run the mission plan again. Now we see a new workspace has been generated. We have the original view command and the plot that we added before, and we've added a data table window showing the spacecraft's epoch and its orbital state over time. Next, go back to your control screen, and we're going to add another plot command. Again, you can either drag and drop this plot inside the while loop using the list of GUI-based script elements, or you can type this command into a FreeForm editor. The plot will show the spacecraft's elapsed time since the beginning of the mission plan, the Sun-Earth vehicle angle, and the spacecraft's subsatellite latitude and longitude location. We'll also add a map command, which you can do by dragging a view command into the mission sequence and then changing the view type to 2D map, or again, just type map spacecraft 1 in a FreeForm. Once you've done that, then go ahead and run the mission plan again. I'll add this plot command using the plot command editor, which is found in the list of script elements. Double click on the plot, and for the x-axis I want to have the spacecraft elapsed time. On the y-axis, the first series that I want to show is the spacecraft Sun-Earth vehicle angle, which I can find by typing S and then scrolling down until I find SEV. Then to add more series onto the plot, I just click the More button, and I want to plot the spacecraft latitude and longitude. Next, I'll add my map command by dragging and dropping a view command, double-clicking on it, and changing the view type to a 2D map. Now I will save the mission plan again and run it. And you can see that now we have 5 different output windows being generated: the 3D view, the 2D map, and our 2 plots, plus our data table report. Next, we're going to practice generating a report file by adding another report command, either using the GUI or using FreeForm script, to enter the following report of the spacecraft shadow times property to a file called shadowtimesreport.txt. Once you run the mission plan again, you can find that file saved in the same folder where your mission plan is saved. I'll add my report command into the same FreeForm section that I was using for the previous report command. I'm going to report out the shadow times method, which the description points out will determine the entry and exit time and the duration of a spacecraft's pass through a shadow. And again, I'll save and run my mission plan. We can see that the shadow times report file that was generated indicates entering and exiting the Earth's umbral and penumbral shadow. Take a minute to make sure that you can find this file on your machine and that it matches the content you see here. The last piece of this hands-on problem is to color code the spacecraft depending on whether it is in light or in shadow. We're going to use a simple if statement to change the color of the spacecraft's tail, and it's easiest to do this in a FreeForm script editor by typing in the if and else statement that you see here and modifying the spacecraft.color property. You can see we're using a utility called Color Tools to easily change the color. You can choose from any of the colors that are available. I'll do this by adding another FreeForm section to keep my mission sequence organized. I'll label this new FreeForm color code the spacecraft and enter the if statement. Make sure to save your mission plan and run it again. Keep an eye on your 2D and 3D view windows and confirm that the spacecraft tail changes color depending on whether the spacecraft is visible from the point of view of the sun. This completes part 1 of our FreeFlyer Fundamentals training video. Please continue on by watching part 2 and part 3.